A warm good evening to one and all present over here. Today we have the 60th QCrete webinar in association with ICI Kochi for the improvement and development in the concrete technology. So I personally thank QCrete for joining hands with the ICI Kochi for promoting this venture. Today there is a special day for us because we have a very special topic to talk about, because we all of us know that the production of cement leads to a lot of environmental issues. 1 kilogram of cement production will cause almost 800 grams of carbon dioxide production also. So that's a real challenge. So all the civil engineers or the research in the area of cement chemistry is looking for a product which can be sustainable and environmental friendly. So one of the most discussed development in that area is LC3 cement or low calcium clay cement. Lots of works are going on around the globe. So we have the right person to talk about that topic today, Dr. Vishalashi, and he has a vast experience in civil engineering, teaching and research. So she is the right person. So in his busy schedule also, she was willing to spend time with us to discuss about this innovative material and technology. So I, on behalf of QCrete Concrete and Indian Concrete Institute and all the participants present over here, I welcome Dr. Vishalashi to this program. And we have engineer Kaushika here. He is the backbone of this program, always working around to get new areas and people for the discussion. So when a webinar causes 60, it itself is a big number. So he is the man behind us. I welcome engineer Kaushika to this program. And
thank you. Thank you, Dr. Elson John. I will just formally introduce Dr. Vishalakshi Talapokula. We are very happy and we are privileged, I can say, from QCrete Readymix to have Dr. Vishalakshi Talapokula today. And it is really a great honor for us that she has accepted our invitation to come and deliver the lecture on this LC3 sustainable concrete today. A small introduction of Dr. Vishalakshi Talapokula. She is presently working as professor and heading the IQAC MU cell at Mahendra University. Prior to this, she was the founding head of the Department of Civil Engineering, Bennett University, Greater Noida. She is graduated from Osmani University, Hyderabad, and she is having PhD from IIT Delhi. Her research interests lie primarily in developing sustainable building materials, structural health monitoring, corrosion of RC structures, smart materials using straw bamboo to reduce the environmental pollution as a part of the ongoing DST Imprint 2 project titled Development of Engineered Bamboo Structures Technology for Modular Rural Housing Towards Sustainable Built Environment. She is having a lot of work she is doing on green wall panels and all through this project. She has done pioneering work in developing physical non-destructive corrosion models for rebar corrosion assessment using piezo sensors, wherein the phases of corrosion and the deterioration can be identified, complementing the existing corrosion techniques. She is having more than 20 years of experience in academics and 5 years in industry, and has guided many UG, PG and PhD students. She has published very high quality research papers, peer-reviewed international journals and conferences. She is a life member of various professional bodies. She is technical committee member of various international and national professional bodies such as ICI and Union of Laboratories and Experts in Construction Material Systems and Structures, RILEM. She has received various awards. Among them include Best Paper Award at Corcon 2012, National Civil Engineers Symposium, IIT Mumbai 2013, and ICT RAM 2012. Dr. Vishalakshi has been helping many students, that is especially in the area of research, and she is doing, I can say, pioneering service to the civil engineering community through her research and guidance. With this short introduction, I welcome Dr. Vishalakshi Talakokula for this today's lectures. Thanks once again, madam, on behalf of QCrete, and I also thank all the audience for having been come at this 7 to 8 hour to listen to this wonderful lecture. Thanks, madam. Thank you.
Thank you, Kaushika. Once again, a warm welcome to all the participants attending this talk. Before I start my talk, I would like to thank ICI for providing this platform with the support of QCrete in order to disseminate the knowledge related to concrete. I think QCrete and ICI Kochi is doing a wonderful job, and you can see that this webinar is the 60th webinar, so it shows their perseverance and their consistency in disseminating the knowledge related to concrete. I'm very thankful to both ICI Kochi and QCrete for giving me an opportunity to me in order to present my research topic to the august audience. Thank you Kaushika ji, and thank you Elson ji. Thank you so much for giving me these opportunities. Yeah, coming to my topic, which is LC3, L, and there are triple C's in that. It means that it's a lime. L stands for the lime, and the 3 C's stands for calcine, clay, cement. It's a limestone, calcine, clay, cement. I'll explain you during this journey why this cement is a sustainable, or else why this concrete is a sustainable concrete, and why the future of, and why this can be the future for our concrete solutions. I'll be talking about that in detail. Let me put it in the presentation mode. Yeah, can you see the slides in the presentation mode? Yes, ma'am. Neelam? Yes? Okay, thank you. So the flow of my presentation will be like this. I'll be talking about why need of sustainable concrete. I think all the participants are aware of this, but I'll just give a glance of my perspective of why we need a sustainable concrete. And then once we have identified that there is a need for a sustainable concrete, then we have multiple solutions for that. Multiple solutions in order to have a sustainable concrete. Then the question arises that why limestone calcine clay? What is that speciality in limestone calcine clay which fits into the good solution for our sustainable concrete? I'll be talking about that. Then the availability of calcine clay, which is the prime most important for becoming a sustainable alternative sustainable concrete. And what are the challenges, if at all we are proposing a new concrete? What are the challenges and the opportunities in manufacturing the same? And then always we have, as humans, we always have that key. Whenever something new comes, we always try to compare it with the old one. So similarly, what is this limestone calcine clay? How it fares with respect to the our OPC and other blended concretes? I'll be talking about their strength properties, mechanical characterization, durability properties, etc. And at the end, I'll take you through the journey of the practical applications of this limestone calcine clay concrete in whichever parts of the world this concrete has been already been used, and what are the projects which are coming up or already had built with this material. See, always whenever the concrete word comes into the frame, it always comes with the saying that concrete is not a green material. So what I feel is that concrete is not a green material is partly true and partly false. I'll give a detailed explanation of why I say that it's partly true and partly false. I'll just hold this question for a while. When the slide comes, I'll again come back to this question. And when we say that concrete is not a green concrete, which I say is partly true, then what is the solution for that? That is the reason we are listening, or else I'm giving this talk to the August gathering. So I'll be talking about that. When we talk about the concrete, I think all the participants know that if you want for the modern societies, for any infrastructure development or for a society to be developed, okay, it requires a built environment, and we don't think of any built environment without a concrete. It is unimaginable for any one of us. It's the hard fact that without cement-based materials, it's hardly we hardly imagine any built structure which is being built upon. The reasons are many. I have listed some of the reasons why concrete is a go-to material. We all know, and I've listed some of them, because it's economical, versatile, local material. With the use of local material, you can build it in any shape beautifully, etc. and etc. That's the reason. Because of all these reasons, we know that concrete is a material which is very widely used just next to water. It is the first man-made material which is very voluminously used just next to water. When we say just next to water, you can imagine how voluminous is your concrete which is being used. And because of that only, there are many innovations which are coming up in the concrete, and it's changing the concrete attributes. Earlier, maybe in 60s or 50s, it was a 4 constituent concrete. It was only made up of 4 constituents, but now we won't imagine a concrete without 6 to 7 constituents. So that's how the concrete attributes have been changing. And also, not only the concrete is a go-to material for any built environment. Okay, in order to sustain the, or else in order to meet this sustainable development goals, or else the society goals, we require concrete. Okay, it means that by building a resilient structure, we require concrete in one way or the other. And in order to build that resilient structure and meet some societal goals, for example, I've listed some of the societal goals here. That is the Sustainable Development Goals of US, or else addressing housing shortage, or decreasing costs from natural disaster, etc., etc. We require concrete. And if you look into the UN Sustainable Development Goals, all the 17 goals, if you carefully look into each one of them, the infrastructure is very critical to meet the Sustainable Development Goals. And there is a publication in Nature in 2019. It says that infrastructure is either directly or indirectly influence all the 17 Sustainable Development Goals. Not only these 17 Sustainable Development Goals, it directly or indirectly influences 121 out of 169 targets. That is 72% of the targets are being linked to infrastructure. And we all know that infrastructure means concrete. Now, this slide gives an answer to a statement that concrete is not sustainable, else concrete is not green. Why I say this figure? Just decouple the material from the amount of volume it is being used. Just look into the material as a material only. So if you look into that material, decoupling it with the amount in which it is being used, then if you see that concrete is to your extreme bottom left and your plastic is to the extreme top right. And this graph which I am showing is the embodied energy per kg and the embodied CO2 which it emits. So since your concrete is at the bottom extreme left per kg, it has less embodied energy and less embodied CO2 when compared to the other materials. When compared to your clay, glass, steel, plastic, aluminum, bitumen, etc., etc. They're all above the concrete. It means that concrete is a low impact material. But why people keep on saying that concrete is not sustainable, not green, etc., etc.? They are very true in saying that because the amount which it is being produced, it is just now we have seen that it is just next to water. So you can see the voluminous amount it is being produced. Because of that volume, it is becoming a not sustainable or else a not green material. So that's where we have to look into that volume we can't stop. We have seen why concrete is important in my previous slides. We have seen for everything you need concrete. That we can't change that amount of volume with which it is being produced. So what we have to do is we have to see some technological solution where we can make it a sustainable one. So for that to happen, if you look into again, if you want to look into how much volume the concrete is being produced, okay, this graph shows the volume of cement, the blue one, which is being manufactured, and the red one, the crude steel, with respect to the population. If you look into the population growth in the last 65 years, if you look into, it's only threefold. The population has grown only threefold. But the concrete manufacture, it is more than 34-fold. It has been grown. And the growth rate is much higher than the other commodities such as steel, etc. Okay. That's the reason there's a large per capita availability of cement, which has improved our living standards in most of the world. And if you look into, compare some statistics, in 2015, it has been given that the total mass of cement which is available per capita is 626, which is higher than the amount of human food consumption. So these are just the statistics which give an impression about how much concrete we are using. And this also gives us the same concept to understand that how much is the production of your concrete with respect to the other materials, other building materials. Okay, so if you see the other building materials, copper, aluminum, etc., etc., the cementitious material, so it is the highest produced one. So now, if you want to achieve the greenhouse gas targets, concrete is the solution. Okay, and what is the solution? The technological developments in the concrete in order to reduce its CO2 emissions. Okay, so with minimal infrastructural changes, how we can adopt the latest technology in order to provide a sustainable concrete is the key takeaway. And this, I think many of us know that key water constants of concrete, how much does they emit the greenhouse gas emissions. This picture gives that thing. I think we all know this. Let me screen. Now, LC3. What I say is LC3 might be a good solution for the problem. How? Before going to tell how, this is what is the journey or evolution of the LC3. It has started in 2014, where there has been a lot of exploration of the calcine clays, which has led to the development of LC3. Then later on, the Swiss agency has supported a projects on ternary blended with limestone as well as calcine clay. Then EPFL has taken that global project forming a consortium of different people from India. There were IIT Delhi, IIT Madras, Tara, etc. They formed a consortium in order to develop this LC3. Okay, then the Swiss agency has funded the development of this LC3 and taking forward this. Then the testings have been happened, and presently now it is commercialized in various countries around the world. During the fag end of my journey, I'll show you how it has been commercialized, in which countries it has been commercialized, and what are the projects which are using this LC3. So this is what was the evolution or the journey of the LC3. And then the RILEM is an international professional body which looks into the construction material. It formed a technical committee. I'm a part of that committee, including 33 academic partners and 15 industrial partners. The main aim and the objective of the committee was first to compare its chemical characterization, mechanical characterization, durability aspects with that of the OPC, and then look into the standards and develop the codal requirements, and then create awareness related to the LC3. Now coming to LC3, or else coming to the concrete, as we know that we have just now looked into how concrete has become one of the go-to material, and it has not become like that just by a chance. It has not become just by a chance. If you look into the availability of the material on the earth, so these are the 8 elements, key elements which are available, and among them we all know that if you look into these oxides, the hydrates of these oxides are too soluble, which will not contribute to the strength of the concrete. And the other 3, this ferrous, magnesium and the calcium, they are too low mobility. So the reason they cannot contribute. Only the elements which contribute to the strength are these calcium, silicon and aluminum, which are the most useful ones. Okay, so these calcium, silicon, aluminum, we all know that they make up 90% of a typical cement. Okay, and then in this, the calcium oxide or the silica oxide, aluminum oxide system, the only reactive material are the calcium silicates or the calcium aluminates. So this is the concrete. That's the reason it is mostly used one. Okay, and we all know the problem with the concrete is the chemical reaction which I have shown in the slide, which accounts for 60% of the CO2 emission while manufacturing the Portland cement. So that is related to the producing the clinker. So if we can reduce that clinker, and we all know that no large volume concentrate sources of calcium other than limestone is available. Okay, so if you want to reduce the emissions, okay, it is exactly the reason why there is a significant CO2 emitter, because we have to provide the clinker, and by we need to decarbonize it. Okay, and this is also a cause of optimization optimism also, because it is clearly possible to reduce these emissions in a relatively inexpensive way, simply by changing the composition of cement. That means the clinker is the main culprit, so reduce the clinker content. Then if you want to reduce the clinker content, or else if you want to look for the other solutions, the other availability of the supplementary cementitious materials. As I told you that if you want to make the concrete green, there are different solutions. Why only LC3? This is what is the slide. Okay, why only LC3 is, if you look into the availability of the other supplementary cementitious materials, that doesn't meet the demand of the concrete production. If any material which has to meet the demand of the concrete production, it needs to be available abundantly. So if you look into the availability, the other SEMs, they doesn't fit into the availability. It's the limestone and calcium clay which are abundantly available and can be a probable solution to our problem. So as I told you, there's no magic solution. Okay, the solution is, if you want to replace cement with any other material, that material should be very much abundantly available. And if you look into the earth's crust and see, it's a limestone and the calcium clay which are available very abundantly on large parts of the world. Okay, and if you also see that the use of calcium clay in order to substitute the cement is not anything new. It already has a large history. If you look into if you observe the Bakra Dam construction, okay, we have used the finely grounded calcium clays from the Shivalik hills, locally called as Surki. So that understanding of substitution of the calcium clay is already there in the history. And not only in India, the practice of substituting the calcium clay for clinker is practiced since long time. So if you look into, these are the list of the project where there was a substitution of calcium clay with respect to clinker. And the answer to why calcium clay cements? So this is the answer: because clays, especially those containing kyanite clays, they produce reactive materials when calcined to 500 to 800 degrees centigrade. And we know that the clay reserves are so vast and unlimited compared to the amount of cement which is being produced. And if you look into the India and China with an established ceramic industries, we have plenty of substantial reserves of clays, which are overburdened or underburdened from the existing quarries. So if you can exploit all these reserved, okay, there will be an enormous potential to increase the global supply of these calcium clays. And this slide shows the availability of suitable clays in and around the world. And if you look into, there are many parts of the world where you can see the availability of suitable calcium clays which can be useful. Now, what is a major innovation in LC3? The major innovation is, we have seen that calcium clays are already used as a replacement to cement, but the percentage of replacement was very low during the early days. But now in LC3, the percentage replacement is very high. It talks about 50 to 60% replacement of clinker. In place of clinker, we can use the limestone and the calcium clay. Okay, so without any reduction in the mechanical performance. In the following slides, I would be comparing the mechanical performance of both the concrete systems, but without reducing any mechanical or the durability aspects, without compromising on that. If you can replace higher replacements of this clinker, that's what is a major innovation of the LC3. And the other thing is, the kyanite content which is needed for the LC3 is much lower than the pure kyanite. Pure kyanite, which is being used for the ceramic or the paper industries. So in order to, there's no need for the LC3, the clays which are used in LC3 contain pure kyanite. Okay, so in India, if you look into, there are abundant amounts of low-grade clays exists as an overburden or an underburden of the existing quarries. So we can use all these clays so that there is neither any requirement of new quarries, nor we are going to deplete any agricultural soil. Just we are using the overburden of the existing clay quarries. And also with as we know that if these clays need to be calcined at a temperature of 700 to 800 degrees, which are much lesser than what we use for a clinker manufacturing. Hence, we use less fuel, obviously will lead to less CO2 emission. Okay, and also if you see the process of calcining the clays, It doesn't emit CO2. But the other case, if you look into the clinker manufacturing, that is the most CO2 emission phase in the cement manufacturing. So it is this is otherwise. And the important advantage of using this calcined clay cement is we can produce or manufacture the same cement, LC3 cement, with the cheaper or similar production cost, and with using the same equipment in the cement plant. There is no need to have a major overhaul of the cement manufacturing plant. Okay, just we need to add the calcination plant in between. That's it. With the existing cement manufacturing plant itself, we can produce this LC3. And if you see, if you can produce the LC3, there would be with a 50% reduction in clinker, and you can see 100 kg of LC3 bag just reduces 50 kg of CO2, 20 to 30% lower than the Portland cement emissions, because there is a reduced clinker, reduced emissions, reduced use of greenhouse gas. And the other important advantage of using this technology is existing equipments can be used. As I told that the plant, it doesn't require any major overhaul. Just need to add one calcination the equipment in that plant. That's it. Then there is a lower cost of production. It is because of the reason that we have reduced the clinker content, reduced fuel consumption, and then reduced production costs. The other advantage of using the LC3 is it's a very known technology for us. It's not new. The system of calcined clay and the limestone used in the cement is not anything new. We already know the synergy between the limestone and the calcine. The chemical characterization or the chemical process of adding the calcined clays or the limestone in the cement is a well-known process, and it's very well established. Okay, so LC3 only optimizes the synergy between the two already known chemical system. We already know the chemical system between these two. Okay, that synergy is being optimized using the LC3 technology. And resource efficiency is also there because we use low-grade clay and limestone, which doesn't require any opening of new quarries or deplete any agricultural soil. So as a result, LC3 is a very attractive and feasible option to satisfy the environmental and the development objectives. This is the proportions of LC3, and if you look into this Portland cement, which contains 95% of clinker and 5% gypsum, then if you look for the blended cements, you have the clinker percentage, which has been reduced by using some of the other SEM, and then gypsum. Then we'll have the LC3 system. The last two bars are the LC3 system, where we have 50% reduction in clinker, adding the limestone 35% and 15 calcined clay 35% and 15% of limestone, or else reduction of 65% of the clinker. So we can have high replacements of calcined clays and the limestone with respect to clinker in this LC3 technology. And if you want to compare the hydration properties of LC3 with respect to the ordinary Portland cement, okay, there are additional reactions which occur when compared to Portland cement. These additional reactions, what are they? Is the ternary blend. The ternary blend is the clinker, the limestone, and the calcined clay. Okay, it reduces the amount of CaOH produced by Portland through dilution. So when we add limestone to calcined clay in the ternary blend, instead of the monosulfoaluminate, it forms hemocarboaluminate and monocarboaluminate. Okay, what does this phases do? This phases, the change in these phases, they have a better pore space filling effect or the pore filling effect. Since it has a better pore filling effect, obviously it leads to better mechanical characteristics and better durability characteristics. And also the metakaolin in the calcium clay reacts with the pozzolanic material, consuming the portlandite and forming the cache. So we have an extra cache which is being formed. And if you look into the global phase assembly of the hydration products of PC and LC3, okay, generally both look very much similar. Okay, the hydration products of PC as well as the LC3 both look similar. There's not much difference between these two systems. That's the reason we say that there's already a synergy and it's an established system. Okay. As I told you that the carboaluminate hydrates are the main AFM phases in the LC3. Okay, and this is mostly similar to all our blended modern blended cements. Now comparing the strength characteristic, that is a compressive strength of the LC3 with respect to ordinary Portland cement. This graph shows the kyanite content, the percentage of kyanite content, okay, and the compressive strength for different days. The bottom one, if you look into, even though you increase the kyanite content in the clays, there is much difference in the compressive strength. And the increase in the kyanite content in the clay has its effects at the later ages. The topmost graph sees, if you look into or observe, there is a vast difference between the clays which contain the high kyanite content and lower kyanite content. So if you want a higher strength in your concrete at a later day, the higher kyanite content would work. Yeah. So this is the same graph, but exaggerated so as to show that this red line shows the strength of an OPC. Okay. If you the second graph shows the variation of the strength with the kyanite content at 3 days, and the red line shows the OPC strength. So if you want an LCC strength comparable to the OPC, then you need to have higher kyanite content at 3 days. If you want a 3-day strength comparable, we require higher kyanite content. But if you look into the top graphs, okay, with only less than 40% kyanite content at 28 days, we will be able to achieve the strength incomparable with the OPC. So we don't require a high kyanite content in our clays in order to achieve a strength comparable to OPC at a later stage. But at early ages, if you want to compare with OPC, then we have to go with high kyanite content. And this graph shows the flexural strength of the LC3 as compared with the OPC. And if you observe it, they are very much comparable to each other. The flexural strength as well as the bottom graph shows the Young's modulus of the OPC and LC3, and you can see that both are comparable to each other. And this graph shows the top left one sorry. The top left one shows the tests carried out by different people comparing the strength of a OPC as well as the LC3, and you can see that all these values fall in the range of the OPC, and they are very much similar when compared to the OPC strength related to flexure, related to tensile strength, as well as the elastic modulus. This is the temperature which the OPC is going to exhibit during its hydration time. And when you look into the LC3 falls in between the OPC and the blended ones. The OPC has the highest temperatures. Okay, the LC3 falls in between, and then the blended ones. And this is the porosity. As I told you that the change in the phases which are being formed during the hydration process of LC3, that is, instead of monoaluminosulfate, sorry, monosulfoaluminate, there are hemocarboaluminate and monocarboaluminate phases which have been formed. And because of these phases, there is a good filler effect happening in the LC3 system. And that's what it shows in the porosity also. The porosity is very less compared to the OPC, and since the porosity is less, it has a good resistance against the chlorides. And you can see the total chlorides with respect to depth for an OPC and an LC3 concrete. The LC3 concrete has much lower chloride contents across the different depths when compared with the OPC. And this is related to the carbonation. As we all know that the blended cements, the carbonation resistance when compared to OPC is bit low. The same problem is with LC3, but people are working since it a lot of research is going on in this LC3 system. People are working how to improve this resistance related to carbonation. And this is the alkali silica reaction, the expansion. If you look into the LC3 system and an OPC system, the expansion of OPC is comparatively low with respect to the ordinary Portland cement. It has a very good resistance related to alkali silica reaction. And these are the sulfates. If you look into the sulfates with respect to the depth of the specimen, you look into LC3 has very low sulfates penetration with respect to the depth of the specimen. And coming to the field application using LC3, the first field application happened in Cuba. There was a house built at Santa Clara. This is the house which is being built with LC3 system. The entire house was built with LC3 system. And then later, there is a industrial production at Dadri. They developed LC3 blocks. And then this is a demonstrative structure. There is a Swiss building in Delhi, which is being built with LC3. And it is being claimed that around 7 tons of CO2 saved in comparison with the existing structures. And then this is a full-scale sculpture which is being built with LC3. It's a 50 meter cube LC3 full-scale sculpture called as La Tenaza, which is built very recently in 2019 in Cuba again. And this place where it is built, it is a demonstrative project in order to see the durability aspects, because the place where it is being built is having the most aggressive environment, which is in the coastal areas of Cuba. And related to the commercialization, recently Heidelberg Materials has invested around 55 million euros in France in order to develop this LC3 production. They have started a pilot project in Ghana, and now already they have started a pilot project in Ghana, and now they are investing in order to start a plant in France. And this is a small video given by Holcim, where they are saying that they have invested in LC3, which reduces the CO2 by half. So where we are replacing the clinker, as we know that clinker is made by heating limestone and other materials, okay, during which there is a lot of CO2 emissions are been happening. So because of this region, we are using the clay which is heated at half of the temperature of the clinker. Thereby, there is no CO2 emission during its transformation, and as a result, we get a reactive mineral called calcium clay. And how we are going to use that material calcium clay? We can start by sourcing the kaolinic clay from local calcium clay is very reactive, so we are going to cool it, and then we are going to add with the other component, that is the gypsum and the clinker, and then supply it. So this is how the production is. But Holcim, what they have done is they are using their proprietary technology done, we call Proxima Tech, which reduce further. They are using the bio-based alternative fuels and also some waste heat energies. Thereby, the end result is they are getting 50% less CO2 than the industry standards. So they are putting the calcium clay to work in order to decarbonize the construction. So this is how the Holcim clay has come into the picture in order to develop the LC3 in commercialization. So this is the progress of LC3 throughout the world. Okay, there are some ongoing projects, ongoing LC3 studies have been happening, and in some places already the production has been happened. There are some projects. These are the list of projects in Africa and in Europe where they have used LC3 in order to develop these projects. For example, the projects in Africa, in Angola, the projects in Europe, with Lafarge, France, it has first launched its calcium clay cement unit in France very recently, in fact, 2023. So this is how slowly it is gaining pace in commercialization also. So that's it from my side. Thank you so much, and I would be very glad to answer if at all you have any questions or the queries related to LC3. Thank you.
Thank you so much, madam, for such a wonderful session. Now it is a question answer session. First question is, can you please share your opinion on utilization of Montmorillonite instead of clay in LC3, asked by Mr. Achyuta Kumar Reddy.
I didn't get you. What is that material instead of LC3?
Montmorillonite.
The Montmorillonite, yes, they are different. As I've given a graph which shows the different percentage of clays and different clays of different purities. It all depends on the purity of the clay. Okay, but for the LC3, we doesn't require high purity clays. Okay, in order to get a comparable strength with respect to OPC. So yes, we can use them.
Thank you, ma'am. Next question is, what is kyanolite content? Asked by Nikhilesh Kamishetty.
The kyanolite content in the clays, in the LC3 clays, is less than 40%. But if you want high strength, then the kyanolite percent has to be increased.
Thank you, ma'am. Next question is there any code and provisions for testing of LC3 cement? And is there any proven results available for durability of the structures built with LC3 cement concrete? What precautions need to be taken? Asked by Mahendra.
Yes. As I mentioned that the professional body RILEM has constituted a committee in order to develop these codal provisions. We are working on that. Okay. In India, still we don't have any codal provisions. Okay. And in some of the parts of Europe, they are in the process of standardization and providing the codal requirements. Okay. So in the due course, I think we also will develop will get the codal provisions related to LC3 cement. Since it is a commodity, unless we have the codal provisions, I don't think we no manufacturer would come forward in order to manufacture this cement. So yes, there are already a draft which is being sent to Bureau of Indian Standards by IIT Delhi Professor Shashank Bishnoi. I think he's already working on that. Very soon, I think we'll hear the provisions, codal provisions related to LC3.
Thank you, madam. Next question is, what is the behavior with admixture? Asked by Shailesh Gupta.
Behavior with admixtures, the superplasticizer dosage, when we have, see, these are all the results which I'm telling you is based on the experimental studies conducted in the lab. So when we have conducted some experiments in the lab, so we found that in order to manufacture this LC3 concrete, the SP dosage, the superplasticizer dosage requirement is high when compared to that of an OPC. So we found to require a high dosage of SPs. We observed that there is a high requirement.
Thank you, madam. Next question is, what were the grades concretes investigated by you? What was the fineness CaO and calcined clay? Did you compare the diffusion coefficients of OPC and LC3? Asked by Dr. V. Kameshwar.
Yeah, the fineness, etc. I don't remember the values, but if you look into the fineness of the clays are much finer. Okay, and the diffusion coefficient, the chloride diffusion coefficient, as I've shown you, when compared to the ordinary Portland cement concrete system and an LC3 system, the and compared with that of an OPC system, the mass loss or the rate of mass loss of the rebar was much less compared to that of an OPC system, because the chloride diffusions are low and with reference to the depth of the specimen, the chloride concentration, the chloride contents are very low compared to that of an OPC.
Thank you, ma'am. The next question is, difference of setting concrete comparison with Portland cement and LC3, initial and final setting time of concrete, asked by Razi.
Initial and final setting time of this LC3 concrete. LC3 concrete has a what you say, delayed setting, which we have observed in our lab compared to that of a Portland cement concrete. It had got a delayed setting.
Thank you, ma'am. Next question is, how does it affect if we use more amount of LC3? Does it helps to achieve more strength or vice versa? Asked by Sanjeeva.
See, the experiments which we have conducted has been restricted to LC360, that is 60% replacement of that of clinker. There are few experiments which are going on for higher replacement. Since we haven't got promising results, or else the results have not been established yet, so I can't answer that higher replacement above 50 or 60% would lead to the same strength comparable to OPC or not. Okay, that I cannot answer now without any substantial results in hand. So 50 to 60% replacement levels have been already proved in the literature.
Thank you, ma'am. Next question is, what is about workable of LC cement in concrete?
Workable, it coming, as I told you, in order to make the concrete workable itself, we observed that there is a high dosage of superplastic which needs to compare the workability of LC3 with ordinary Portland cement. The SP dosage in LC3 is higher for the same workability.
Thank you, madam. Next question is, can we replace OPC completely by using LC3 material? Asked by Vinay.
Yeah, that's what I told, that higher replacement, the experiments are going on. So I can't answer now because without any substantial results. Whether we can go for much higher replacements, no, as of now.
Thank you, madam. Next question is, at the time water added to concrete, how much heat produced to LC3 cement type concrete?
Yeah, I've already mentioned in that graph. If you compare the heat generated or the heat evolved in the LC3 system, it is much less than that of an OPC system. Okay, but more than that of a blended system. Okay, so LC3 system falls in between related to the heat evolved. OPC on the top, the blended on the bottom, and in between is the LC3 system.
Thank you, madam. Next question is about lifespan and durability when compared to OPC. Asked by Asfar.
Yeah, durability aspects I've already explained that it has good resistance to chloride, induced corrosion, and it has good resistance when compared to the OPC. The chloride diffusion levels are low. The rate of corrosion in the rebar happening inside the concrete is low, and the sulfate resistant, it is having a good sulfate resistance because the expansions are very low. Okay, the sulfur ingress is also very low. Coming to the carbonation induced corrosion. Okay, this is the same problem with all the blended cements which we have. LC3 is also facing the same problem, that the resistance is bit lower than that of the OPC related to the carbonation.
Thank you, madam. Any more questions can be asked to technical@QCreteIndia.com, and we will forwarding to madam. And now I handing over to our MD sir, Shelly Fernandez sir, for vote of thanks.
Good evening, friends. I'm Shelly Fernandez. Can you hear it? Hello.
Yes, sir. Yes, sir.
Yes.
Yeah. Good evening, friends. I'm Shelly Fernandez. Now we have come to our end of this another very interesting and excellent topic we could convey to our all the audience today. The talk was on LC3 sustainable concrete for the future by Dr. Visalakshi Talukola. Dr. Visalakshi was been able to put the topic in a very simple way, and I'm sure this product will be the product for the future actually. As we all know that availability of OPC in the market is very less, and market is in search for an alternative cement actually. And I hope this LC3 can become the cement of the future actually. So today's lecture was explained in a very simple way, and hope our audience, both from the academic and the industry, will be vastly benefited from today's very simple to the basic lecture, which was conveyed by Dr. Visalakshmi. Thank you very much today. Thank you, Doctor. Thank you very much for your very interesting lecture. Actually,
Thank you. Thank you so much.
Yeah, coming back to my duties of vote of thanks. First of all, I thank Dr. Visalakshmi for the lecture, and also for coming on to QCrete and ICA webinar series, and which will be very vastly benefited to all our audience, which attend in huge numbers. Even though most of the people have started this webinar during the Corona time, difficult times which we passed through Corona. We also started it, but what we found is that most of them have actually stopped telecasting this webinar series actually. But we are continuing with it because of the vast demand from our audience to continue with this very, very topic which crosses the, most of the people attend all over India, and most of the time it is from outside also people are attending to this particular webinar series actually. So we hope we'll continue this particular, this one and reach 100 one day actually. So 60 is also a good benchmark actually. So thanks a lot for all the executive committee members of Indian Concrete Institute Cochin, the president, the secretary, and all the EC members who have been very, very supportive in conducting this particular webinar series. And also to Kaushika and his team for continuously pursuing me and taking this program forward actually. Thanks a lot. Thanks to all our audience who have been giving us the support and giving us the strength to go to conduct more and more lectures. So this is, with this, we come to the end of this particular lecture and hope to meet you again for the 61st lecture with a new topic. Thanks a lot. Thank you all. Thank you very much.
Thank you. Thank you so much. Take care. Bye.